Hi, everyone. Welcome to this lecture video for section 2.3, which is about two variable data and also rates of change, but I'm not going to talk much about rates of change. We'll focus on two variable data. So we've been talking about equations that have two variables, like y equals 2x minus 7, and learning how to plot those on a graph. I can tell you, for example, that this one has a y-intercept of 0, comma, -7, because if x is 0, that goes away, and y is -7. If x is 1, it becomes 2 minus 7, which is -5. If x is 2, it becomes 4 minus 7, which is -3. And we could connect all of this and see that actually we have a straight line. So what we've done here is we've gone from the symbol to the pictures. I did use the numbers, I just didn't write them down. Right, I said if x is 0, y is -7. That was a numeric representation. And then I went to the graph. Two variable data is similar, except it usually starts with the numbers, because data often is referring to numbers. But the idea is very, very similar to when we start with equations. I didn't write the words in the middle of the last one. Let me write that. Okay. So for two variable data, we're going to start over here with numbers, and we might see our numbers arranged in a table. Where when x is 0, y is 5, when x is, this is not the same example, by the way. When x is 0, y is 5, when x is 1, y is 3. All right, and we have our data laid out, and that's what we're starting with. And we want to end up usually with symbols, and we can use any of these other representations to help us get ultimately to the symbols. We could jump straight to symbols for numbers, and that's a skill I want you to work on. But working through graphs or through the words are useful as well. So let's work through the words first. Okay, so I look at this table and I notice that when x equals 0, y equals 5. So I'm starting at 5. And then I also notice every time x increases by 1, y decreases by 2. And what we've done by saying that y starts at 5, and every time x increases by 1 and y decreases by 2, we have now turned this numerical representation into words. I'm describing what's happening instead of showing you with numbers. And I can go from the words to the symbols if I remember that lines are usually written as y times this, I can't remember if we've talked about slope. We're talking about it now. Y is equal to some slope times x plus some starting value. I'm going to go back to my other example. Notice we have a -7 on the end, and that's the starting value for y. And the 2x means every time x goes up by 1, y goes up by 2. So we can use that same idea here. Y is starting at 5. So I'm going to add a +5 for where it starts. +5 for where it starts. And every time x goes up by 1, y goes down by 2. So I'll do a -2x. And if I were to draw this as a graph, the point 0, comma 5 tells me I start here, and then when x moves to the right by 1, y moves down 2, right? Because the point 1, comma 3 is on the graph, and so is the point 2, comma 1, and 3, comma -1. And I have my y-intercept is 0, 5. That's where the +5 comes from. And I have the x changing by 1 and the y changing by -2. That's where my slope comes from. So that's pretty nice when our data looks like this, when it's an easy step, 0, 1, 2, 3. But how about if our data is not so easy just to visualize? So as an example, one thing I could do is I could make sure I don't actually ever start with an x equals 0. Let's just start at x equals 3. And let's see, 4, okay. But then I could also, instead of just going up by 1 each time, maybe I could go backwards, right? It's just x's. I can pick whatever x's I want. I'm doing a little math in my head real quick. That's a -13. And then I'm going to jump up ahead again, but this time I'm going to go to 6, which gets me to 19. Right, and I don't know about you, but it's pretty hard for me to look at these patterns of x's and y's and say, where's my starting value and how much do I change by? So is this even a linear relationship? That's really hard to tell just looking at the table. So instead of looking at the table, let's change it to looking at pictures, because if there's anything that's easy to see if you're working with the linear relationship, it's looking to see if it's going to be a straight line. And we can do this on the graph paper, but I'm not the best at drawing. And plus, we have a really good graphing calculator called Desmos that I want you to be using for these sorts of questions. So I'm going to change my screen over to Desmos and show you how to do this using Desmos. All right, so there's Desmos. It's our graphing calculator. We can put functions in pretty easy. I could do y equals 2x minus 7. That was one of my examples. And there it is. There's the y-intercept at 0, -7. And every time I increase x by 1, I increase y by 2. But not only can we put equations in, we can also put tables in. And to do that, you press the plus, and you can choose a table right here. And now you get to put your coordinate pairs or your ordered pairs in one by one. You can't see them, but I'm going to put the ordered pairs in. It was 3 and 7. X equals 3, y equals 7. X equals 4, y equals 11. X equals -2, y equals -13, and x equals 6, y equals 19. Now we can't see any on here yet, but what you can do is you can zoom out. And if you zoom out, then you say, aha, yes, maybe that is on a straight line. It looks like it, but again, it's hard to tell because they're just 4 dots and they're pretty far apart. But there's a really nice, easy way to figure out if they're exactly on a line. this little option over here to the left called add regression, it will plot a line that fits your data as best as possible. And you'll know that it's a good line if your formula is these nice big round numbers like 4x minus 5, and if all your points are lying right there on the line. If that's true, then you can be sure, or you can be very confident that you have a linear set of data. This is the symbolic formula that produces these points. And you can test it, and I want you to test it by in Desmos just taking that formula and plugging your x in. So we can do 4 times 3 minus 5, and I got 7, just like I wanted to. The 4 comes from the y equals 4x, and the minus 5 comes from y equals 4x minus 5. 4 times 3 minus 5 is 7. Let me change that x to the second one, which was a 4. 4 times 4 minus 5, that's 11, right there. I can do 4 times negative 2, open a parentheses for that negative 2, and then close it. And you get when x is negative 2, y equals negative 13. And 4 times 6 minus 5 gives you the 19 you're looking for. So the way you can confirm if table data is a linear equation, if it's not something where you can just look at the table and count that way, you can put it into Desmos, and maybe it'll be really obvious that it isn't, but if it looks like it might be, then you press the little regression button that was up here, and it's going to give you an equation, and then you test all your points in that equation. Let me give you an example now of wondering, I might keep it simple on the x values, wondering if I've got a nice linear equation or not. Let's see. Out of 5, 7, well, let's see. Okay. So here we go. Yeah, I look at that, and even just kind of looking at those points, they don't necessarily, they look like they're perfectly in a line, but it's hard to tell for sure. Maybe my eyes just aren't great. So instead, I'm going to come up here to where it says add regression, and I'm going to click there. And sure enough, the line that best fits the data, it's not fitting it perfectly, is it? Those points aren't actually on the line. My equation is maybe another hint, because it sure doesn't look like it's a nice set of simple numbers. But really the key here is to look at your picture. And if your points are clearly not on the line, then it's not going to be a linear equation. All right, I just want to show you one more example because I think it's a good idea to do another example. And this one is from the textbook. So here we have an equation or a table, a set of numerical data, and we want to know if it could be linear and what that equation might be. So let's put these points into Desmos, first of all, just to see if we think that they're probably going to be linear. So I'll do that first. I'm going to have to hop back and forth a little bit. There's a 17 and a 13. Oops. And 16, 8, 3 for the x's. And the y's were 12, 8, 11, 3, and negative 2. Okay. If you ever need to reset your zoom, click the home over here in Desmos. And then you can kind of zoom in and out. Yeah, those definitely look like they could be in a line. All right, we can double check by pressing the add regression. And yeah, those points definitely look like they're right on that line right there. Another little cue is this statistics part down here. If the r squared is equal to 1, then it's on a straight line. But R did this for me. Sorry, Desmos did this for me, which I think is great. I'm going to use it every time. But I also want to show you how you would do it if you used just by hand instead. I'm not necessarily saying you should do it by hand, but I want you to know how. So we had X and Y. It was 17, 13, 16, 8, and 3, 16, 8, and 3, and then 12, 8, 11, 3, 3, and -1. All right, so here's how I would approach this. The first is I would sort my X values. Is if you're asking me to do some kind of analysis on raw data just with my eyes and a pencil and paper, I have to make it as easy on me as possible. And the way I can make it the easiest is if I sort it from smallest to largest. 3 comes first, then 8, then 13, then 16, and 17. And notice when I'm sorting, 3 and -1, they move together. So it's still X equals 3 and Y equals -1. I move that whole ordered pair up there together. That's my first step. Now I'm just going to measure, I'm going to count how far I have to get between each X's. So X goes from 3 to 8, that's up 5. And then it goes to 8 to 13, that's also up 5. Here it goes a smaller step. 13 to 16 is over, only up 3, but that's okay. And 16 to 7 goes up 1. Now I'm going to count how my Y's move. I made an error. I just noticed that should be a -2 paired with the 3, not a -1. So fortunately, I caught that. I never make mistakes on purpose, but I make them all the time. So the key is to be able to catch your mistakes when they don't make sense mathematically. So I sorted from smallest to largest with my X to Y's. Then I counted the change in all my X's. Now I'm going to count the change in the Y's. That changes by 5. 3 to 8 changes by 5. 8 to 11 changes by 3, and 11 to 12 changes by 1. Notice when X changes by 5, Y changes by 5. So the change is 5 over 5, which equals 1. 5 Y's over 5 X's. The next change, the Y over X's, is also 5 over 5, which is equal to 1. And the next change is 3 over 3, which equals 1. And the next change is 1 over 1, which equals 1. All of those changes are the same between any two of the points. And if all of these changes are the same, not the 5 and the 5, but the 1 and the 1 and the 1 and the 1, if all of those changes are the same, that means it's changing at a constant rate. And if it's changing at a constant rate, it's a line. And we can answer the question, does this data come from a linear equation? And yes, it does. And in fact, we know the slope of that linear equation is 1 because that's the constant rate of change. All right, that's all I'm going to say about this section. Tune on back for the next one.